First, our main thread script starts by checking if the web workers feature is available in the browser. The if statement here is looking at the global window object to see if the worker property is defined, which indicates support for web workers. Since web workers are supported, we initialize a new worker by calling the worker constructor and passing in the path to our worker script, in this case, worker.js. This kicks off a separate thread that can run in parallel to our main thread. Next, we post a message to the worker using the postMessage method. This is used to send data to the worker thread to start the CPU-intensive task. The main thread sets up an onMessage event handler which will be triggered when the worker thread posts a message back. The e-argument in the callback function represents the event object. Inside the onMessage event handler, this console log statement is used to print out the data received from the worker. E-data contains the message from the worker. This closes our onMessage event handler function. The main thread script also sets up an onError event handler, which is called if an error occurs within the worker thread. The error argument will contain the error information. If an error occurs, we log the error message to the console. This can help with debugging if something goes wrong in the worker's execution. This closes our onError event handler function. And this else block of code runs if web workers are not supported. It's a fallback to handle situations where the browser doesn't provide the necessary features. Here we simply log to the console that web workers are not supported, to inform the user or developer running this code. This concludes our conditional check for web worker support in the main.js file. Moving to our worker.js script, it listens for the message event using the global self object, which represents the global scope of the worker. The function is called when the main thread posts a message to it. Once the worker receives a message, we log that event to the console, showing the message contents from the main thread. Here, we're calling a function named performIntensiveTask that we will shortly define. This function is supposed to do the actual CPU-intensive job. Once the intensive task is completed, the worker posts the result back to the main thread using the postMessage method on the self object. This concludes the message event handler of our worker. Now, let's define the performIntensiveTask function, hypothetically representing a CPU-intensive operation that might block the main thread if it were not for workers. We start by initializing a sum variable that will store the result of our computation. We enter into a large for loop that will iterate a billion times, just to simulate a heavy computational load. Inside the loop, we keep adding the square root of the iterator variable to our sum. Square root calculations are relatively CPU intensive, which helps in simulating the desired load. This closes our for loop. After the for loop has completed, we return the sum variable, which now holds the result of our computation. And this marks the end of the performIntensiveTask function. The worker script also includes an onError event handler. If an error occurs during the execution of the worker, this function will be invoked. In the case of an error, the worker posts a message back to the main thread that includes the error message. Finally, the worker uses the self-close method to terminate itself after an error occurs. This is important for freeing up resources and ensuring that a failed worker doesn't continue to run. With this, we wrap up the error handling part of the worker script.